what we are going to do is look at a few problems from Project Euler, and this is just me documenting my experiences in solving problems in Project Euler. I had solved a few problems before, as you can see, using a different language, Haskell before, and what we will do today is look at problems using Python. Going from what we see over here, you will notice that technically speaking, is it okay to publish my solutions elsewhere? The answer is for the first 100 problems it is possible, so we will look at the first 100 problems. Okay, and we will discuss the solutions like it mentions over here. So you will see all the steps that I take to solve the problems, and once I have if I am able to solve all the 100 problems, then I will not share anything beyond that anymore. So here goes. So this is my first post doing this. Let's look at the first problem. Oh, the answer is already here. Okay, so the answer is already here, but let's try to solve it using Python. Okay, so if we list all natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Find the sum of all multiples of 3 and 5 below 1000. So let's make sure we understand this problem correctly. Okay, so we will open up Jupyter Notebook and we will say this is problem 1, like that, and let's just copy the problem. Okay, that's the problem that we are trying to solve. So let's see. We need a list of numbers, and in this case we will just look at all the way up to 10. Okay, 10. If I percentage 3 is 0, or I percentage 5 is 0, so that's saying that it's divisible by 3 and 5, and we just say that if we, so it's 3, 5, 6, and 9. So it's 3, 5, 6, and 9. Adding 0 will not change anything. So we can start from 1 if necessary, and then we can just sum this. If we sum this, we get 23, like we see over here. So if instead of going from all the way up to 10, we go all the way up to 1000, like that, then the number should be equal to 233168, which is the number 233168. So yeah, it's that's solving the first problem. I would say that is a success. Maybe we will not create a separate Jupyter Notebook for every single problem, so this seems pretty simple. We will call it problem 1. Okay, why does it have, okay, never mind. Okay, now let's try to get to the second problem. Where's the second problem? Okay, so we can say that we have solved this problem. How about this even Fibonacci numbers? So that's the, so let's go back. Let's multiples of 3 and 5 is the name of, let's put it over here. The name of the problem is multiples of 3 and 5, like that. Okay, the next problem is even Fibonacci numbers. So this is problem 2. There you go. We do that, we call this problem 2, like that, something like that, and let's copy the problem. Okay, let's take a look at this. Each new term in a Fibonacci sequence is generated by adding the previous 2 terms. By starting with 1 and 2, the first 2 terms will be that. By considering the terms of Fibonacci sequence whose values do not exceed 4 million, find the sum of whose values do not exceed 4 million. So you have to make sure that the Fibonacci, the value itself is not greater than 4 million. Find the sum of the even valued terms. So the sum should be the even valued terms. So let's start with the sum. Total is 0, and the first 2 terms are P, I, and J equals 1 and 2, and obviously the first term. Okay, so let's, while true, we are going to go all the way till, let's do the first till 100. So you will say, make sure that we are only getting all the way up to 100. Is 100, like that. Then we want to make sure that we have all the Fibonacci numbers. So 1 is not an even term. 1 is not an even term. So if J percentage 2 is 0, so that's an even term, then we can add it to total J. Okay, and then we advance I and J. I and J equals J and J plus I. This is J plus I and J, like that. And let us say if J is greater than, if J is greater than up to value, wait, okay, it did do something, but I want to make sure that I print I and J at this point. Print I and J, and we see that the values are 1 and 2, 2 and 3, 3 and 5, 8, 13, 21 all the way to 89. So that's good. The sum of the values, print total is going to be 44. Okay, exceed a million. I doubt that's going to be the case. If we do that to a million, which is 1/6, then what happens? We don't want to print every single thing. The answer is 1089,154, and that is definitely not the answer. Oh, 4 million. 4 million. 4 million. The answer is 4613732. So I think we can say that we have solved this problem as well. Okay, so problem 2 solved. We can maybe take one more problem and then call it a day today. Okay, so let's see. Largest prime factor. Okay, so problem 3. So this should be problem 3, and this is called the largest prime factor. Okay, let's see what the problem is. Okay, the prime factors of this happens to be this, this, and this. All right. What is the largest prime factor of the number 600851 blah 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 like that? So we definitely need that number. Okay. Next thing is we need to make sure that we get a set of prime numbers, and we have to check whether the number that we get is in fact a prime. So how do we do that? We need to find the largest prime factor. I think one of the things that is worth looking into is what is the largest prime factor of this. So if you take the square root of n, let me just import numpy. And we do np dot square root of n, then we see that the square root of n is that. So this times this is equal to this, but we want to find something that is smaller than this number, and the first number that is smaller than this number that divides this should be the largest prime. But we can check that. Why? Because it may not be the largest prime. Once we get a number, we have to also check whether it is a prime or not. So let's check whether we can get this number first. So this is something that we can do in Python. Range 10 and -1. 10 and 1 and -1 will go all the way from 10 to 1, and it will decrease in steps of 1. So it goes from 10 all the way to 2. It will not do the last one. So what we can do is we can have a range. We can take the int of this, integer of this, and we can go all the way up to 1 and decreasing in that way. That's the number in range all the way over here. Yeah, and we want to see if n if that n is divisible by n. Print n. Okay, so these are all the numbers that it's divisible by. So it kind of limits the set of numbers that we need to check. So the largest prime factor is the one that will be one of these things. It will be either this or this or this or this or this or this or this. What we need to do is to check whether this is a prime number, and if this is not a prime number, then we need to check whether this is a prime number, and so on. Let's check the answer real quick. If it's not one of these things, then we are way off. So let's check the number. The answer is 6857. Do we have a 6857? We have a 6857 over here. So these numbers are not prime, and this is the first prime number. So we need to check if a particular number is prime, and the way to check for it is very simple. We'll create a function, check for prime. We pass a number n, and we do the exact same thing for I in range int of np.sqrt of n, like that, from that to 1 to in steps of -1. Okay, if we can find a number that divides this by some other number, then it is not a prime. So let us try and divide this. So the number n, if n percentage I is 0, return false. false, and we go through every single thing and we check and we don't find anything, then we turn true, then that is a prime. So this is this, and let's also check for prime and n. If we do that, check for prime is not defined. It's probably a spelling mistake somewhere. Let me copy paste that. Hopefully that will work, and we see that this is the number 6857 is the number that happens to be a prime, and this is the biggest number. So once we should be able to break if check for prime n, then print n, that's all you do, and break. Okay, so it should only print this number 6857, and that is the answer. So that's the third problem. Maybe we can do, I don't know, one more problem and then we'll call it a day. Okay, let's see. So this problem is solved. Let's look at the, so this is what we solved. Yeah, largest prime factor number 4. Let's look at this, and I think we'll do this and then we'll call it a day. Largest palindrome product right here, and let's do this is problem 4. This is largest palindrome product, and okay, so that's let's take a look at the problem. A palindrome number reads the same both ways. So the largest palindrome made from a product of two digit numbers is 9009. Okay, and that equals 91 times 99. All right, okay, that's great. Find the largest palindrome made from the product of two 3-digit numbers. Interesting. So I can do brute force, but I'm trying to think if there is a way of doing this such that we don't have to do brute force. Let me check. Let's start with brute force first. So if we have 3-digit numbers, so those are numbers for I in range, let me see, 100 times 100. 100 to 1000. Okay, so that goes all the way from 100 to 999. Those are all the 3-digit numbers, and you can just do that, this and J, 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 and if you have a number, largest palindrome, see, largest palindrome is a problem, so we can list all the palindromes and get the largest one. I times J string. So just so you know, n, let's say it's that, then that will be the reverse of that string. So that's one way of getting the palindrome. Let's see. If n is that, print n, okay, and there are literally, well, a gazillion of these, but you just need to sort it, right? House equals this, and there you go, and sorted. We should convert it back into an integer over here. All right. Let's do that. Now all pass like that. And the last one is 906609. Let's see what the answer is. 906609. So that's the answer. Okay, so we can say that we have solved this problem. Up till now the problem seems pretty simple, so we will just stop over here and maybe continue another day. Okay, bye bye.